So now we have formed a complex. The complex will be able to, now it's massive complex, will be able to diffuse across that hydrogel again simply by diffusion, because that is a property of the export receptors. They can actually interact and swim through that hydrogel. They will make it to the other side. When they get it to the other side, they will again encounter RAN gap. RAN gap will force RAN to hydrolyze its GDP, and because RAN is now in the GDP state, it cannot keep hold of the export receptor, will let go of it, and the export receptor can no longer bind to its cargo and will let go of it. So the complex dissociates. We have delivered the export cargo to the outside, the protein that we wanted to transport to the outside. We have released the export receptor to do another round of recycling, of export, by coming back in through diffusion. And we've kicked one more RAN GTP, one more RAN to the cytosolic side, not to the outside, to the cytosolic side. All right? So we made the problem twice as bad. Right? So what happens with RAN? How big is RAN? Small. So SAR1, there are small GTPases, right? So it's somewhere around 25 kilodaltons. Definitely small enough to get through that hole back into the nucleus. So it can simply come in by diffusion, where it will be reactivated by binding GTP. Where do we need the most RAN GTP? Sorry, the most RAN protein. Is the protein doing anything on the cytosol? No. It's doing its job inside the nucleus. So if we were just to have lots and lots of RAN on the cytosolic side, that would be kind of a waste. So we actually want it more concentrated in the nucleus. There is a separate pathway that I'm not going to cover that involves grabbing that RAN from the cytosol and shoving it against diffusion into the nucleus. Right? So the RAN is going to be brought back into the nucleus as much as possible. If you stop that machinery, then that RAN will diffuse out. All right? But we're not going to cover them. But there's a recycling mechanism. All right? Yes?
So if there's RAN GDP in the nucleus, it doesn't affect anything, like if it doesn't get activated by GAP immediately?
So, okay, great. So let's consider this RAN GDP that got in by diffusion, and say RAN GAF is over here, but it diffused on this side. Is it going to kind of block this interaction? Possible, right? So what would be, I love that as an exam question. What would be the possibility, so what do people think? Would a RAN GDP that hasn't been yet turned into GTP bound RAN mess the works here? Not, why not? You would care to comment? Maybe?
I don't know. Like, I don't know totally why, but it just doesn't make sense to me because, like, it can't bind to the receptors. Like, it's not going to do anything.
That's the key word, right? So in the GDP bound state, cannot bind to anything in here. So it would be just like a little marble floating around, right? Not doing anything. Of course, if we had lots of marbles, it would be a problem. Right? But just a few by themselves would not be a problem. And eventually, it will become activated by hitting a RAN gap. Great question. Yes?
Earlier on, we had the RAN GTP bind to the import receptor. It caused it to release the protein. However, now when we have the RAN GTP, when the RAN GTP, the export moves outside, when it dissociates from the export because it's now GTP, why does the export automatically dissociate from the cargo?
Yeah, so you could say, I am the export receptor, right? And I want to bind to the cargo. I cannot bind it unless I'm pinched over here by RAN. So now that opens my binding pocket, now I can grab it. As soon as RAN lets go, I let go, right?
Okay.
So it's all through conformational changes.
Okay. So the import receptor can bind the import cargo without,
Precisely.
but the export cannot.
It's the opposite. The opposite action of RAN on the import receptor compared to the export receptor.
Okay.
Yep. Cool. Any other lingering questions? Okay, so a lot of this has been shown through the use of really useful mutations that can be implemented almost in any small GTPAs. So it's important for you to know, because you might encounter this in another field that also involves another small GTPAs. As Dr. Halloran mentioned, there are small GTPAs proteins involved in regulating a whole slew of mechanisms inside the cell. So we go through the regular cycle, right? That we have, if we have GTP bound, the protein is in the functional state, so it can function and interact with other proteins. If it has hydrolyzed the GTP, now it has GDP, is unable to interact functionally with other proteins. So, and we have the accessory proteins. So if we cause a mutation in say, let's just talk about RAN. If we make a mutation in RAN that blocks its ability to hydrolyze the GTP, if we will to bind GTP, be all ready to interact with things, and it will do that, but it cannot be inactivated because it will not be able to break that GTP. So it will always stay on in the GTP bound state. Some people call this the constitutively active state. Always active. Always promoting what it's supposed to promote. If this was a mutation in SAR1, then that SAR1 would always be forming coated vesicles. All right, and would not allow that coated vesicle to depolymerize and release and fall off the vesicle. Was there a comment up there? Yes.
A mutation in gap, would that be also considered dominant active or no, because it still happens just like really slow?
Yeah, so there's a difference. So this part of the cycle is promoted by the gap, but the GTPase has its own intrinsic rate of hydrolysis, so you would not be able to turn it off immediately and fully, whereas this, every single protein that has a mutation will not be able to be turned off. Right? So the effect is going to be in the same direction, but maybe not to the same extent. So I like that. Alternatively, we can have a mutation that blocks the ability of the small g protein to bind GTP. So in that case, we might have a protein that has no nucleotide at all, or that it can bind GDP but not GTP. So in this case, this protein will not be able to be turned on into the activated state. So we could call those a dominant negative mutations of RAN. If this happens in the chromosomal copy of this gene, that cell is not going to survive long because nuclear transport is going to be essential for the cell. But a lot of these mutations you can do yourself by taking the gene, the cDNA for this protein, making the point mutation in the right location. Because these proteins are highly conserved, very similar in sequence to each other, we know pretty much which site in the binding pocket of the GTP you need to change, and in which way to make it one way or the other. Very predictable sequence changes that you can use. Then you take that mutated cDNA, put it in an expression vector, bring that inside the cell, and then now force that cell to produce this mutant protein in one way or another. Right? So you can do it artificially, and then you can ask, what will happen if I have one protein, or what will happen if I have the other mutant protein, right? Which is what I'm going to ask you now. Awesome, so you are very strongly answering C, that the import receptors will not bind to their cargo, because that's what happens when you bind that active. So the fact that it's a dominant active means that it's a protein that has bound to GTP, cannot hydrolyze that GTP. That is why D is wrong. It would not contain GDP, it would bind GTP and not hydrolyze that GTP. RAN will be able to, will be in and out of the nucleus because it can diffuse in either direction. And the receptors, once they are bound by that RAN GTP, will not be able to bind any new cargo. And because RAN with GTP is stuck to that receptor because it has GTP, now that receptor is unable to go through multiple rounds at all. Right? So that will happen anywhere in the cell because now all the cell will contain this activated mutant RAN. Let's do one more. Oh, no, sorry. Wrong question. No, I don't have it. Okay, so there's one more in your handout. So you can do that while you're studying this stuff. All right. So any lingering questions? So I want to show you this little video that is part of the textbook, if you got the video.
Nuclear import and export can be directly visualized in living cells that express the green fluorescent protein GFP fused to the gene regulatory protein NFAT. NFAT is normally localized in the cytosol and excluded from the nucleus. But when the cytosolic calcium concentration is raised, NFAT migrates to the nucleus. This is done here experimentally by adding an ionophore that allows calcium to enter the cells from the medium. Upon removal of the ionophore, calcium levels return to normal, and NFAT is exported from the nucleus. Re-addition of the ionophore triggers re-import of NFAT.
Okay, so here we have a protein that is able to go in and or out of the nucleus depending on conditions. So if the cell receives, and this is true for a lot of transcription factors, many genes need to be expressed only when the right hormonal signal comes into the cell. So you want to inactivate the transcription factor in some way. The easiest way is just to keep it in the cytoplasm. When the right hormone signal comes to the cell and say, now make whatever you're supposed to be making, now that transcription factor is brought into the nucleus to do its job. And now once the job is done or the signal is removed, that transcription then needs to be moved out of the nucleus again. Same protein, all right? So there's a variety of ways you could accomplish that. But the simplest one is to have one protein, one transcription factor, that has both an NLS and an NES, right? So it has both sequences, both signals in different places of the protein, right? Now, if they're both exposed, what's going to happen? Exactly right. I'm going to go in, oops, I'm going to go out, and I'm going to go in and out all the time, right? So some proteins actually do that. Some proteins are going in and out of the nucleus for other reasons that we don't have time to go into. But this case is either one or the other, right? So there are many, this is true for many proteins, and there's a variety of ways in which this can accomplish. And this diagram illustrates some of that, but I don't